everyone. Here we are back with Geometry, Chapter 7, Section 3, proving that a quadrilateral is a parallelogram. So in the previous lesson, these were some of the things that we looked at. We know that a parallelogram, by definition, has two sets of parallel sides. And then Theorem 7.3 told us that the opposite sides in a parallelogram are congruent. 7.4 told us opposite angles are congruent. 7.6 that the diagonals bisect each other. Now, if we want to prove that a quadrilateral is a parallelogram, if any of these are true, then the quadrilateral is a parallelogram. So those are usually the converse of those theorems. So the definition of it, if we have two sets of parallel sides, it's a parallelogram. Or if opposite sides are congruent, then it is a parallelogram. That's Theorem 7.7. The opposite sides converse. If the opposite angles are congruent, then it's a parallelogram. That's the opposite angles converse, 7.8. If diagonals bisect each other, then it's a parallelogram. That is 7.10. The diagonals converse. So that's just the converse of some of the ones we looked at in the previous lesson. And then also 7.9 is if a pair of opposite sides is parallel and congruent, right? Because if these two are parallel and they're the same length, then something that connects at the end here has to be parallel to another line that connects at the other side. So these are the strategies we can use to prove that a quadrilateral is a parallelogram. All right, couple of examples here. Here we have at an amusement park, a ride, kind of a swing, where this rotates around. And we know that DC is parallel to the ground. So this stretch right here is parallel to the ground. Explain why the moving platform AB is always parallel to the ground. Well, here we have AB is 38 feet and DC is 38 feet. So those two are congruent. AD is 16 and BC is 16. So those two are congruent. So this is a parallelogram. No matter how this moves, these sides aren't going to get shorter. So it's always going to be a parallelogram. That means AB is always going to be parallel to DC. And since DC is parallel to the ground and AB is parallel to DC, AB is also parallel to the ground at all times. All right, finding side lengths here. We want to find a value that would make this a parallelogram. Okay, in this case, we're not given that it is a parallelogram. We want to find something that would make it a parallelogram. Well, we have to find x and y. We have two variables here, so we have to find x first. We know if this should be a parallelogram, then this side has to be congruent to this side. So we have to set those two equal. X plus 9 would be equal to 2x minus 1. Solve for x. Subtract x from each side. And that cancels out the x here. Add 1 to each side. And we get x is equal to 10. Now plug that in right here. We get 10 plus 7. This side is 17, which is the same as y. Therefore, y is 17. Here's a door of a place in England. I wonder which way this opens up. This seems like it would just swing up. It would be kind of tedious to open. Anyways, this building has been leaning for quite some time. And now it looks like this forms a parallelogram. Do we know for sure that ST is equal to UV? So SV, sorry. Do we know that this side is equal to this side? How do we know that? Well, we know that ST is not only congruent to VU, but is also parallel. Therefore, this is a parallelogram. That is based on Theorem 7.9. If opposite sides are congruent and parallel, then it's a parallelogram, and therefore these two sides are also congruent, and by definition of congruency, SV is equal to TU. All right, for what value of x is this a parallelogram? Well, in a parallelogram, we know 710 tells us that if the diagonals bisect each other, then it is a parallelogram. So if they bisect, that means that this would also be congruent to this section right here. So 5x, we need to set that equal to 3x. All right, subtract 3x from each side, add 8 to each side, and we get 2x is equal to 8. X is equal to 4. So if x is 4, then this is a parallelogram. All right, and identifying a parallelogram in the coordinate plane. All right, here's my handy-dandy reference guide right here of the different ways that I can determine this. Now, in the coordinate plane, you're given coordinates, or if you're given the graph, it makes it even easier. I'll show you a couple of methods that you could use, and I am going to use the definition. All right, showing that they're parallel is going to probably be the easiest one here. I could show that they opposite sides are congruent. I would have to find the distance between each, so I'd use the distance formula. I find slope is a little bit easier, so I'm going to do that one. If you prefer the distance formula, you could do theorem 7.7. So I will check to see what is the slope between A and B. All right, from 3 to 5, I'm going up 2. From -3 to 2, I'm going up 5. So it's up 2 over 5. That's one way. If you have the coordinates, you can find the slope, or you could just count. Up 2 over 5. So from D to C, I went up 2 over 5. That's another way of finding the slope, so also 2 over 5. All right, so I know these two have the same slope. Okay, so I can say this is parallel to this one. Now I need to find the slope of these two. Very easy on the graph. I can see down 3 over 3, so it's -1. And this is also down 3 over 3, so also -1. And therefore, this is parallel to this side, and hence, by definition, two parallel sets of sides, I know that's a parallelogram. And that's about all the fun we can have with this lesson, but check back again next time for another fun lesson in geometry.